Okay.
Yeah.
You just have to delete.
So if you are planning to follow, so you have here two things you can download. Is the source of the notebook and some intermediate files. This is the URL. The Wi-Fi password for here is, give me a second, I will add it there. But it's 401 capital W capital G Georgia.
Take over yours? It will be there in 30 seconds. Sorry.
All right.
Perfect. It will be there. Is it back? Back for you.
So if you download this file here, then you will have all the data to run the whole notebook. That takes like a day to run.
We've got that set up. Or you can angle it however you
So the notebook has 32 cells. We are going to see 3 cells today. And so those 3 cells need these files here. It's only 6.2 megabytes. But if you want to run the whole notebook, you need this file that is 400 megs.
Should we use like a more powerful remote machine, or is everything going to work fine on our local?
So I've been running this with 8 gig of RAM. This one has 16, but it's only a 6.2 meg compressed file, so it's not that bad. But support vector regressions take a long time to run. So I'm going to show you the results. I'm not going to run it during the meetup. But we're going to look at the code. So the code I'm sharing is code that I will put in GitHub when I finish the book. But this is not the final version, so don't put it online. That's the only thing. You can use it as much as you want. I mean, it's licensed, but it's open source license, but it's still not finished. Let's say like a little less than a year. I mean, I have to finish it in the next 2 months and a half. But then I don't know how long the publisher will take to edit it.
So
Cambridge University Press.
is she here? Are you doing that?
I'm going to do it because Mona has to help bring people upstairs from the lobby.
Okay. So we've got good time.
Just say when.
Thank you. Yeah, can we add one more thing? The link to the OneTech.herokuapp.com.
Sure, I don't understand what you said, but I'll happily add it.
You know, wherever you added the Wi-Fi password?
Yeah, give me a sec. Yeah, so yeah.
Yeah, you just an H1 tag. And
That'll do. I can't see.
Oh, sorry.
There. Yeah, I'll quickly do this.
If that looks inconvenient, the alternative is to log into the virtual machine and modify it using VI. So this is really convenient.
Data science? Yeah.
That's for the streaming?
No, this is for the
joining.
The joining, because then people are
Sure,
clueless,
sure.
and we don't put it on meetup.com because a lot of bots started
I see.
attacking the team.
Join the Slack. Sorry? So I have to have it finish my side around end of February, and then how long they will take, I don't know, but I think it should be around 6 months to fully edit and everything. So I hope middle of next year. The source code, I have to have it finished I think 3 months after I deliver the file, so the source code may be earlier than the book. And the link to the source code is in the notebook.
How long have you been writing it?
2 years. It started more like I wanted to learn more about feature engineering, and then now I have to finish writing.
How long until it self-destructs? Is there any chance we can download it when we get home?
Of course.
We're gonna wait for about 5-10 minutes, and then
Yes.
Yeah, I don't think the render version will run on will look anything on a phone, and it's quite a big page. But so this is the whole monster, and it is quite long. Finished that this morning. And I had to change a whole section because on the dry run I realized that the algorithm I implemented was not the one that was in the book. It went out?
sorry, yeah, it goes when I try to.
Okay. The good part is that when I implemented the algorithm that was in the book, it actually improved.
Vancouver. So welcome to DevHub. A lot of you might be really not familiar with this space. It's because we actually took possession of our new office space just this summer, and we started rolling out everything in the fall. So basically, DevHub Vancouver is a community space for developers in the city. And so how we do that is, if you take a look at when you guys came through that door, the entire floor is actually DevHub Vancouver, and the space is kind of split out. So what we want to do is support a developer throughout their entire life cycle of being a developer. So if you were interested in becoming a developer, you'll see that Lighthouse Labs has everything going on. We run all our boot camps, our 10-week boot camps. We've got part-time courses at night. And of course they have their own meetups and workshops that happen. We also have co-working space, which is why you'll see lots of developers working really hard. We currently have about 13 different companies that work out of our space, so that if you were a startup, early stage startup, and you needed a space where you can kind of work alongside people that are working on similar things, then we'd love to have you join us. And the whole point of us also having co-working space is because for these startups who are now looking to hire potentially junior developers, they literally just walk across the elevator lobby and see all of Lighthouse Labs' new grads. So they kind of get that first glimpse into the people that are coming out looking for jobs. And then of course we now have many different areas of our floor that we host meetups as well. So DevHub, we have weekly lunch and learns, we do monthly workshops on different topics, everything from JavaScript all the way to design thinking to startup fundamentals. So if there's ever a topic you guys are interested in learning a little bit more about, feel free to reach out. But we also wanted to make this space open to community friends. Trying to, always looking for a venue in town's a bit rough, so we always want to open our doors so that by default, if you think of the word developer, whether it's an event, you're looking to hire, or you're looking to become one, you can always just come to the 6th floor and literally yell the word help. And one of us will be able to come out and help you. So that's the whole kind of premise behind what DevHub is. So I'll leave it to you guys. Thank you so much for coming. Feel free to reach out if you guys have questions. But
Thank
over to
you.
you guys.
Yeah.
Thank you so much.
Can we put the
Yep.
Hi, welcome. Thank you for coming in tonight. My other co-organizers decided to ditch me and go to NIPS this year, just last week. So
Next year, NIPS is in Vancouver.
next year NIPS is in Vancouver. So NeurIPS, yes, sorry, yeah, NeurIPS. So thank you for coming. I'm Osama. I help these guys organize the meetup. I work with Streamlabs. We're a streaming startup. Thank you, Pablo, for coming in. Just some logistics before we start. That's the Wi-Fi password. You might need it tonight. We've got a Slack community. It's called vantech.herokuapp.com. That's where we can channel around production machine learning, data science, machine learning, computer vision, all sorts of stuff. So it's a pretty active community, and you can reach out to Pablo, myself, and a lot of other people who are here tonight there. So, about logistics, fire escapes are marked with that green mark in case there's something. Bathrooms are marked.
They're just in the elevator lobby.
They're in the elevator lobby. So usually what we do is we do a really quick 30-second intro so that people are settling in, downloading files. So it would be awesome if we can just go around. We don't have a mic tonight, so let's just start from here. And then the format is, what's your name, what do you do, what's your interest in the talk tonight or in this meetup in general. Thank you for coming in. Do you want to start?
Sure. Yeah, my name is Peng. I work at Bezier. It's a tech company in Yaletown, and I'm the solution architect. I'm just interested in machine learning application in general.
I'm Annie Yin. I do AI, data science, computer algorithms in a startup. Here I am, 3 years back, we organized another meetup, data science was super good, so look up for us.
My name is Adrian. I'm looking to learn more about data science and AI stuff, starting from the ground up.
Also, if you're looking for a job or if you're hiring, just feel free to announce that.
That's it. Peter Heinrich, just interested in the topic, so decided to make my way out here from Langley.
Oh.
Bit of a trek, yeah.
My name is Bart. I'm a freelance software developer. I'm currently using machine learning for personal projects, and I want to find out more about feature engineering from web pages. So, who knows?
My name is Leo. I am working as a machine learning engineer in SkyHive startup in Vancouver, doing natural language processing mostly.
Well, Dinesh. I work at Ella, data analyst. And I'm out of I'm Wayne. I'm a data scientist at a company called Fingerprint Studios here in Vancouver.
I'm Malma. I actually work in a visual effects company, industrial light and magic. I'm just learning all the machine vision and CNN and data science stuff, so expanding into different areas is more interesting.
Hi, I'm Mark. I just finished my master's in computer science at SFU in deep learning, NLP in particular, and soon will be looking for work.
Hi, I'm Marcus. I'm working as a data scientist at Teva for Vancouver.
I am Tom. I'm a software developer, industry and machine learning.
I'm Branka. I work at CMAX as a computer vision engineer.
I'm Jason, formerly a software engineer, formerly at Hootsuite, currently at Google, looking to learn more about deep learning specifically. I've used statistical inference and stuff a little bit, but getting more into deep learning.
I am Sudipto. I used to be in the US, working in academia, doing research, working for organizations like that. Where I'm funding, so I moved to Canada. I'm looking to join industry as a data scientist as well.
I'm Lynn Zoom, and I'm a web engineer at Magic. I'm interested in web, especially in cloud engineering.
I'm Tyler. I'm like a data scientist slash business intelligence consultant. I'm interested in data science. I like doing like deep learning for textures and stuff like that. It's kind of interesting generally.
I'm Veronica. I'm a business system analyst, and I'm interested in data science.
I'm Vincent. I'm working as a assistant company, and I'm curious about the results to see if it's something that I could help.
I'm Alex. I'm a solution operations, and I'm interested in data modeling, artificial intelligence, and
My name is Oleg Popovsky. I'm DBA for Mary Solutions, interested in data science.
I'm Tim, software developer here in town. Interested in machine learning, but not teaching myself lately.
My name is Sri. I'm working in the field of computer design for Screencast.
My name is David. I'm working as software developer for Pablo, created for the Great Cup.
Peter, I'm software developer and I'm just trying to learn more about this.
online instructors, and I'm here just to learn about machine learning and data science. I think that's
I am Mahmoud. I am a software developer and data scientist.
Alex Pamir, project engineer, Intrinsic Technologies, machine learning enthusiast, and find some software that will run on company's hardware.
Timothy Lee.
I'm Paula. I'm a software developer at SAP.
I'm Jessie. I'm doing my PhD in chemistry and physics. And my research is on machine learning and neuroimaging, focusing on hyperscaler.
And Nicola, I'm a data analyst enthusiast and get a lot of funding. So.
Hi. Hi, my name is Jessica. I'm currently working on launching my deep learning app, and I'm also a friend of Pablo's, so here to support him, and always glad to learn about something new machine learning.
Hello everybody, my name is Forrest. I'm a data engineer at Khan Academy. Recently I'm actually learning about feature engineering for graphs, so would love to learn from you. Thank you.
All right. So.
Good. All yours.
All right. So for the people interested in deep learning, there should be another talk for that because this has no deep learning on it. Don't leave the room yet. And so what is going to be on this talk? It's 4 parts. We're going to talk a little bit of concepts of machine learning and feature engineering, particularly the cycles, a little bit about exploratory data analysis and error analysis, and introduce the Wikicities dataset. Then over that dataset, I'm going to talk about 3 different feature engineering techniques: simple feature discretization, feature selection using multiple information, and target rate encoding using AutoFold. This is part of material for a book I'm writing that should come up next year, and I give a lightning talk last month that you can look at the slides if you're more interested about the book and why I'm writing the book, what type of content will be there. So I have a undergrad from Cordoba in Argentina a long time ago, and also a long time ago I did a PhD in Columbia, but the one in US, in New York. And afterwards, I went to IBM Research, and I work on the Jeopardy team to build the show system. And there I was actually working on the machine learning and the feature engineering part. And that's where I got interested on the topic. And in general, I'm not a research scientist on machine learning particularly. I mean, my research has been mostly in question answering, information retrieval, natural language generation. But I use a lot of natural language feature engineering and machine learning in my research. I also have a consulting company here in Vancouver, and we're putting together some products on the summarization space. All right, so giving this talk is quite challenging because the backgrounds are so diverging in the audience. So I need some definitions to make sure that we all have a common background. So in this talk, we're going to be talking mostly about supervised learning. Yes, so it's learning classifiers, trying to learn something that it's basically a function extrapolation. You take some input points and some target, and then you're trying to learn that function. However, for the purpose of feature engineering, we like to distinguish between the input data as raw data. So somebody comes to you and say, well, this is the data I have, and I want you to learn this function. So in general, that stuff has instances, has rows, and has a target class or a target number you're trying to learn. But from that raw data, we want to obtain features. Yeah, so we want to focus on that step of going from this raw data, from this Excel file, to actual features that your machine learning will work well. And why is that? Well, we're going to come a little later, but that's why, to me, I consider the machine learning cycle, I'm going to expand this shortly, as much more than just take a model and run it, yes? So instead of starting from you just run your model, I want to convince you that you should look at this raw data and do a step of exploratory data analysis. Look at the raw data, look how each of the different columns behaves on the data, how these columns correlate with the target class, get some better insights, and from there, pick the model. Yes? So, and also, from that analysis of the data, pick the evaluation metric we are going to use. So then, when you go to transform that data into features, you already have some idea about how this data is behaving. And then the rest of the machine learning cycle goes as usual. You take that features, you split them into a train set and a test set. You take the train set, train your model, and then you take your test set and you evaluate it with the metrics you have designed beforehand. And then you get your results. So, as I was saying, the exploratory data analysis, the intention is to analyze sets, to summarize the characteristics. is usually done through visual means. You may want to plot things like the correlation between one feature, one column on your data, and the target value. And at this stage, what you're doing, you're formulating hypotheses about the data. Oh, I think this column, for example, has a normal distribution. I think this column will is growing exponentially, so most probably I want to apply a log function to it, and things like that. So in the machine learning case, when you do exploratory data analysis, you are trying to help pick the machine learning model you want to use and the initial featureization. You also want to pick the metrics. And this is an issue where many practitioners just use the metric that come with the software package they are using. Yes, so if the software package gives you F-measure, they use F-measure, yes. And there is plenty of value on thinking seriously about the problem you're trying to solve and finding or designing a metric that works better for your problem. For example, false positive and false negatives are rarely at the same level when it comes to the value of a model. Yes, there are certain problems that can tolerate plenty of false positives, but the false negatives are very expensive. Think, for example, if you're doing anything that involves filtering, yes, then you can tolerate a little bit of false positives, but you don't want to have any false negatives. You don't want to lose any data. But if you are doing anything that is a very expensive thing, like you are going to do a surgery on a patient to extract a sample of a tumor, then you don't want to have any false positives, right? You want to make really sure that that's needed. So this thing called the contingency table, then it helps you lead this type of metrics and also other techniques we are going to see later. When you have regression, when you are trying to predict a real value, then you can take the absolute error, or you can take the square of the error, or the root mean square. So these metrics are quite popular. And this is the one we will be using for the task today. Okay, so there is a technique for doing evaluation that is quite popular, called it cross-validation. Does anybody here haven't heard about cross-validation? Have not heard. Good, because you are most likely not going to understand it from this. Okay, so in cross-validation, you take a data set, you split it into folds, and then you take all but one fold, you train a model on that, and then you test on the unseen fold. And it's very popular because of two reasons. First, if you use cross-validation, you're making sure you're not testing on your trained data. Yes. And second, you have this feeling that you don't waste any data for testing. However, I argue that data used for testing is never wasted. Yes, gaining more insights about how well your model works is actually very valuable. And from the little bit of data that you use for testing, you are not going to really improve the parameters of your model that much. And if you're going to improve your parameter, you're going to change your model a lot for 10% more data, then you have a model that is not stable. And that's a different problem. The other part is that when you do cross-validation, you end up actually having n models. So doing error analysis becomes very complicated. So the other part is that you still may overfit if you do cross-validation. So overfitting refers to fitting too closely to the training data. So that means that you have a model that has failed to generalize. It's doing more interpolation rather than extrapolation. And of course, the rule of thumb is always use a separate train and test set. Yes, but you can still overfit in a more complicated way, because the train data and test data are a sample of your overall population. So you can overfit to that sample. For example, if you're trying to predict adverse drug reactions, and the training data was all collected during the winter, yes, and you find out that the feature that the patient was thirsty is a very good feature. Then when you run this during the summer, well, you will end up having a lot of false positives. And so from that perspective, there is no really silver bullet when you are trying to avoid overfitting. Okay, so we arrived to my definition of what is feature engineering. So feature engineering is a process. Yes, so it's a series of steps you follow to achieve a goal of representing a problem domain. So your main issue when you're doing feature engineering is a representation issue. It's going from this raw data to these features. I consider it similar to the framing problem when you're trying to solve word problems in mathematics. Yeah, so you can imagine your raw data to be like the word problem statement. And then the features are actually the formulas that you obtain. So you're trying to represent the problem to make it amenable for learning techniques. So that process involves the initial discovery of features and their stepwise improvement. And that's based on domain knowledge. So the more you know about the domain, the better features you can get. And if you don't have knowledge yourself, you can try to seek out to experts on that domain to help you, which is something that we tend to forget quite a bit in machine learning. If you are doing something with mining, resource extraction, natural resources mining, you can go and ask a mining engineer what things will be good feature. And domain knowledge and observe performance. So error analysis is key for doing better feature engineering. So what makes good features? Good features are informative. So the feature describes something that makes sense to a human. That's quite important also for doing the error analysis. They are useful, so it's defined for as many instances as possible. And they are discriminant. The feature divides the instance into the different target classes. And so in feature engineering, you're going to be doing a lot of cycles. This is going to be expanded, so don't worry about it. But one of the big problems when you do feature engineering is that if you do a lot of cycle of feature engineering, you are going to overfit incredibly. You are going to end up having something that memorize your training data to the T, and you're going to have a very ineffective feature set. So in that sense, not over-engineer when you do feature engineering is really important. The best way to avoid doing that is to have a data schedule. So you take all your training data and you split it into little segments, and you go using each of these segments for a cycle of feature engineering. But that's not always possible. So instead of that, what people do is you take a held out there at the beginning of the process, and they call it like a final test set, confirmation set, and then you test on that at the end of the process to make sure you haven't overfit too much. However, if you test on that data set and it has overfit, what do you do? So what I'm proposing is that when you do the feature engineering, you try to make two feature sets. One that is the one with more optimal results, and a second one with more conservative features that you say, okay, these features, if this other one fails, then we can use the other ones. At least you don't need to really build the whole feature set. You can have some intuitions about which features you want to put there, and if the first one fails, then use the second one. But then what I'm proposing is that you split your raw data into two sets. But see, here you're not splitting the feature, you're splitting the original raw data. Because what you are changing is the transformation from raw data to features. So the held out is at the raw data level. Then you iterate many cycles of this machine learning cycle we saw on the previous slides, improving the features. And at the end, you end up with these two different feature sets, a conservative one and an optimal one. Together with them, you have trained models, and you have results on a test set during the development. You use these feature sets to featureize the held out data on both sides, and then you evaluate these features. And that gives you some two results. And then, having used that chart flow diagram in many years, then if the optimal result is better than the conservative, then you have an overfit, you are good, you can use it. And otherwise, you have the conservative one as a safety measure. Okay, so before we go to the wiki sites, the last part is a little conversation about what error analysis entails. there is a big temptation when you do machine learning to just look at the metric. You get obsessed with getting that number and improving it. But metrics are very opaque if you want to improve your features. So what I'm advocating is for an error analysis where you start looking more into particular cases. Yeah, so you try to identify instances or classes of instances that contribute to the error a lot. And we're going to see today an example of that. And for that, then you use the contingency table. And of course, to be able to go from the errors to the actual instances, you need a machine learning system that has been instrumented, that has kept all this information available for you to do error analysis. So from there, then you can drill down on different hypotheses of reasons why these errors come to be. Once you have this hypothesis, you go back and see whether this hypothesis will account for a lot of error, because you don't want to optimize things that don't need optimization. So basically, after all this error analysis, what you're trying to do is a feature drill down. Yes, you want to group poorly performing features, because simpler models have less parameters, so the same data can be used to obtain more informed parameters. And you also want to expand good ones. So for that, you take a feature that works and you make changes to it. Yes, or you try to combine them. And we're going to see examples of that today. And you can also, while you are doing this, you can go back to your original raw data and try to propose new features. Moreover, you can go back to where you got your raw data and ask them to give you more data. You can take your raw data and add other data sets to improve it. Okay, so the Wikicities is a data set I'm putting together to exercise different feature engineering techniques. So it's the same problem predicted from properties that we're seeing today, from textual description, historical data, and satellite imagery. And the idea is just to take a city and predict its population. Yeah? So what we are seeing today is predicting the population based on the properties that appear on DBpedia. DBpedia is a project that transformed the info boxes, the boxes that appear next to each page on Wikipedia, into a semantic web graph. So each graph is represented as a set of triples, and they use the nomenclature subject, verb, object. So for example, property like the name of the leader of the city of New York is a mayor, is expressed as a triple New York City leader title mayor, but New York City is represented as URL http://dbpedia.org/resource New York City with underscores. The literal is colon mayor at n, indicating that it's in English, and the relation is this ontology leader title, and these relations come from an ontology. So it's a multi-graph with as many nodes as literals and Wikipedia pages are there. So this is a large data set. Also, this comes from Wikipedia, so it's all written by different people. So it's very, very noisy. So even though it's ontological, that will give you the idea that it's very clean data, it's actually very noisy ontological data. So in the first part is doing this exploratory data analysis. So we want to see how many relationships are there, how the cities look like, what information is available for each city. At that stage, we also look at, there is value on inverse relations. So not only relations that a city is the subject, but also a city is the object. So things that end up in that node. We can also want to see how many relations, how many values a relation can have, yes, and how the population information is expressed. So these are the first 12, 14 cells on the notebook are the error analysis. And there, I, for example, take 10 different cities at random and graph them using GraphViz. So here you have a city that is Unadilla, Georgia, and you have different relations. For example, the elevation is 130, I guess it's meters over sea level. And it has two elevations. Yep, I guess the city has 2 points. Here you have the population density, the population total, so it's 3,700 people live there, and it has all these relations. That's pretty nice. That means that for all these cities that appear, there is information. This is the area code, this is the offset from the time zone, and it has 2 time zones because you have the summer time and the regular time. And then you have this inverted relation. For example, this is the place where the Dooley State Prison is. Yes, so it's at the receiving end of the location relation.
Sorry.
Thank you. Okay, so from this analysis and from lot of cells, we get this idea for a basic featurization. It's very clear that the number of times each of these relations occur has value on it. Like, just to begin with, how many of these edges are there give you a good intuition about how many people live in the city. You know, a city that has thousands of links is most probably a much bigger city than a city that has very few links. But then, a city that has, for example, is the location for multiple things, most probably it's a much bigger city than one that has few. So therefore, for each of these relations, we add a hash count feature that contains how many of that relations is available. For numeric relations, like area total, we can use them directly. And for non-numeric relations, then we have to see what to do with them. Without going into doing some natural language processing, a simple thing to do is just to look at whether there is a small number of values that cover most of the things. Yeah, so, and then there is a cell there that does all this relation count analysis, and you find that, okay, 21 countries cover 80% of the cities. Yeah. 59 departments and so forth, so on. So in a sense, these relations can be expressed as features with this number of columns each. Or, I mean, if what you end up having is, for example, a column that says UTC offset is -5, and that column is 0 or 1, depending whether UTC offset is -5. Make sense? This is called one-hot encoding of categories. The next step is to look at the target value. The target value is population. So if we plot the populations, we get this graph, which is very common for human-related things. Yeah. So when you see a graph like that, then you immediately apply log. Yeah. And when you apply log, in general, you use log base E or 2. But in this case, it's very nice to use log base 10, because that tells you how many digits is the population of that city. And when you do that, you realize that our data is wrong. That I was using cities that come from a file that says cities with at least 1,000 people. But here you can see you have 0 and you have 2 and 3. So from here, from this exploratory data analysis, you find that the raw data was incorrect to what you expected beforehand. I'm saying that you have certain expectations and hypotheses about your data, and you want to look closely to make sure that the data behaves that way. So after these things are actually coding errors on Wikipedia. There was a city that has 1 million people, but it was put with dots instead of commas. And therefore, the extractor extracted that there was 1 person living there. And OK, so then we start looking into what model we can use. So here, we take this feature that we think is valuable, how many relations each city goes into, and we apply it with a regressor, with a support vector regressor using Gaussian kernels. And we obtain this graph. So this line here is because it's one feature and it's a support vector machine. So this is basically the support vector. Yeah, but you can see that the curve, that is this curve here, is the figure is kind of tracking the curve. And you have a root mean square error of 0.61, which is basically you are getting one digit, one order of magnitude from the CT. It's not such a bad error for one feature. The question is a problem with the SVR? The SVR is a bad system for this, or is a problem with the feature? For that, we can plot the counts versus the population, and we obtain this graph. So that shows that, okay, there is a little bit of a signal, yes, but it's not a very strong signal. So from here, conclude just to use SVR. By the way, you feel free to stop me and ask me questions or stuff, or comments, or this stuff I'm presenting is extremely open for debate in a sense. These are my opinions, but they are just that opinions.
Excuse me, I can't see the figure from here. What are the axes here?
Yeah, so the axes are number of relations, and this is the log of the population. So this is the log of the number of relations, this is the log of the population.
And how are you concluding that SVR, we should go with SVR here, based on this?
So this one seems to track, yes, but if this was like a perfect line, then this is a very poor result. But this is far from being a good line. So looks like it's extracting all the information that is here to take.
If it was perfect, it would just be dots all on a
Yeah.
single straight line.
Yeah.
Okay, so there's a tendency there. But
There's a tendency, but it's quite a cloud.
Yeah, okay.
All right, so
Sorry, actually.
yeah.
One more question. So let's say if, so you started with SVR, just wondering why you decided to start with SVR, and if SVR failed, where will you fall back to next? Do you have a list of where you go?
Sure. I most probably then I will just switch to a discretization and a classifier on the discretization, and we'll go with the random forest because of the variety of features. Which is most probably what we'll do for text. I mean, I'm working now on the text side.
Okay.
And the SVR is just to fit a curve, basically, a function.
The SVR fits a curves with blobs.
Do you have an intuition on the choice of kernels?
Choice of?
Kernels for SVR.
The
You said you use Gaussian kernels, is it?
oh, kernels. Yes.
Do you have intuition for the choice of kernels?
Yeah. So I think this problem is quite non-linear. So I wouldn't use a linear kernel for this. But you're fitting the curve with blobs. Yeah. So the blobs have two parameters, the c and the epsilon. So those ones are very sensitive here. If you don't fit them correctly, then you get nothing. You get like a line. And so in that sense, that will be the two kernels I will use for this type of data. You do have graph kernels that you can use, but that will be kind of out of the point of what I'm trying to do with this chapter, that is show how to add information from these to regular feature vectors. All right, so if we do the featureization I described here, yes, the counts, the one-hot encodings, and the numerics, you get this full curve, which have a RMSE of 0.41 and looks quite nice, except for these parts. Yes, we say, wow, something goes really weird at the end. I mean, this is these curves are sorted by the number of people. So at the end, for some relatively big cities, the system thinks they are super big. So that gives us an idea where to focus our error analysis. So the error analysis, then I start plotting which are the bigger contributors to the log error. And what we get here are some cities that are slightly over-predicted. And then some cities that are under-predicted. So the ones that are italic are under-predicted. And so then for the ones who are under-predicted, I start looking into the Wikipedia pages. And the Wikipedia pages have things like citation needed for or this number is the number for the whole metro area, not for the town, or this one has an extra zero, or so at the end of the day, the small cities are actually, the system is more correct than the Wikipedia source. But the big ones, on the other hand, are cities that, for example, the case of Dublin, you know, like you look at the amount of inlinks that Dublin has for in the English speaking, like the amount of English speaking Wikipedia worth it, people born in Dublin is huge. But Dublin is not that big because of the Irish diaspora. In the same way, for example, Nicosia is one of the oldest cities in the planet. It has 4,500 years of history, but it's divided between Turkey and Cyprus. So 55,000 is only half the population of the current city, and it's not like a lot of people are moving to Nicosia due to that. So it's but it has enough history and enough links to it to have 6 million people. So those cities then become quite interesting to study, and these are then the ones who contribute the more to the absolute number of the error. So for these 10 cities, then I do, and only for them, a feature ablation. So it's a technique where you take the system, you drop one feature, you retrain the system, and you apply, and you see how the error changes. Yep. So if you have, in this case, I have something like 400 features, then you train the system 400 times, and you test it on these 10 cities 400 times. This, of course, takes a long time to run, so this is done in like a small percentage of the trained data. But even though it's a small percentage of the trained data, the results are quite stable. I mean, I ran this a few times. And what you get from here is that the counts are really hurting you. Yeah, so it seems the counts are really quite responsible for the errors for these cities. Yes?
So when you remove the feature, do you train the whole model for the whole city or just only for those cities?
Yeah, so you take a, well, you can use the whole training data. Oh. You use all the training data because these are cities on the test set.
Oh, okay.
And then I just testing them on these 10 cities. I mean, normally you do feature ablation to understand the behavior of each feature, but here I'm using feature ablation for error analysis. Which, what I'm interested to see is, okay, these people are hurting my error. I want to see how they behave just for these. If you take too many aggregates, then things get very lost. So then from here, I see all these counts, and I can either drop the counts, or I can try to not make them so wild. I can, for example, threshold and say, okay, you know, Dublin has so many, is the city of so many things that maybe after 1,000 I should just drop it at, you know, put a max. Instead, I can say, oh, I took the log of the people, of the population. I should also take the log of the counts, because I'm kind of trying to do a regression with things that are not similar. And when you do that, then this curve is actually better than the previous one, but it's scale different because now it doesn't have the outliers. And the RMSE goes down to 0.3556. So all these feature engineering cycles not necessarily should help, but in this case they do.
Can we just drop outliers?
Yes, but if you're going to drop outliers, you have to have a reason to drop outliers. I mean, also, you cannot drop outliers from your test set. I mean, you can drop. Well, I mean, if you're going to drop them from your test set,
you can detect them. You can drop them
I mean, you can do an ensemble system that say, for these ones, I'm going to run a separate model. But if you're trying to predict whether a customer will leave the service or not, then you will just drop those people altogether? All right. Okay, I mean, I believe that there are outliers that you drop and outliers that you don't, and these belong to the category you don't. But yes, in some cases you can drop outliers. Okay, so now that concludes the bit getting into what data set we are using. So for the two techniques we're going to see later, we need they operate over discrete features, not over features that are continuous. So we're going to see this technique for feature discretization. It's a very simple technique. The idea is that you have a continuous feature, like a population, like the target class, and you're trying to transform into town, small city, and megalopolis. Yeah? And of course, when you do discretization, you get an error. So because you're replacing an exact number like 2,513,170 by 2,500,000. Yeah? So in that case, you incur an error of 13,000. So why we want to discretize? Well, one reason is that you want to train a classifier rather than a regressor. You have an idea that a classifier will do better, then you can discretize and then train a classifier. And the other part is that you can use algorithms that needs a contingency table. And now we go here. So the way I have structured this code is so that each of the cells can be run independently. So that's why it has all the imports, and then it does something and save everything to disk, and then so you can load them and run them just that cell. So this cell uses the features after applying the log on the counts, and so then you put all these into two NP arrays, the train data and the test data, because we want to measure the discretization error. So the algorithm is very simple. You just take all the populations, you sort them, and then you split them into half and half and half and half, and that gives you 2 to the n classes. Yeah, and for each of these segments, you take the center as the discretization value. Then you can measure the error of the discretization by saying, well, I have this city with this population, and I predicted as this other number, what is the error I get? So that's the predict number, and at the end of this whole thing, then you get this table where you say, well, we segment into one, so into 2 segments, then you get a 0.7 error. If you segment into 4, no, sorry, if you segment into exactly 1, then you get 0.7. If you into 2, you get 0.44, 4, 0.29, and 8, 0.19. So, like using a classifier with 8 classes would actually get you a pretty nice error.
Wouldn't it be the case the more you go, the lower the error?
Sure, but then the more classes you have. So there are other algorithms for discretization that are much interesting. They normally receive the number of splits as input or the discretization error as input. Yes, and but the recursive splitting is much easier to implement. And you know, the issue is that after a certain point, just the number of splits gets too unwide. And also, I mean, using the discretization error as input is a much effective way of dealing with discretization in general. Okay, so so now that we have a discretized target feature, we can compute some feature utility metrics. So the idea with a singular feature utility metric is similar to training the algorithm on that feature. So at the beginning, when we trained SVR on the total counts of relations, that was a way of saying whether the total counts were a good feature or not. The problem of doing that is that you may have features that are good in some cases, but not really good for all cases. Yeah. So you have a feature that for a certain value of that feature, it really predicts very well a particular value of the target class. And the rest is not that good. But you can expect that the machine learning can use that link to make a better classifier. So instead of doing one feature full machine learning, you look at the contingency table for that feature versus the target class and see whether a particular value is good. And of course, the discretization then is key. So let's take, for example, if you discretize number of people born in a city into 4 classes, yeah? And then you discretize the city also in 4 classes. Now, we are trying to see whether cities that have tons of people born there are more likely to be gigantic cities. So then you make a contingency table. You say, well, how many times this feature with this value versus the others appears with that value versus the others. And so you have 4 observed numbers. And there are a number of metrics you can use. I mean, this is a regular contingency table. You can use chi-squared, t-test, a lot of different things. For this particular data set, I found mutual information to work very well. So mutual information tells you, if you know one probability distribution, how much information that gives you when you are trying to explain the other one. You can think of it in terms of, for example, if you were compressing one file, how smaller it will get if you compress one after the other. So the formula involves the the probability of the 2 events by the log of one over the other. And in the case of a continuous table of 4 columns, of 4 entries like we saw before, it's a closed formula here. And so this is a formula that is pretty straightforward to program. Together with that, you can also use these feature utility metrics to choose certain features to drop. You just put a threshold and say, well, if the feature utility is below this, I think this feature is very bad. The question is how to get that threshold, right? So one neat trick to do that is to inject random features. You take a feature that's completely random, you throw it in, and then you start looking at how your features get ordered, and if some features start having a lot of random features above them, then you say, well, this feature is really indistinguishable from random. And anything after that, then you drop. So in this case, I use 10 random features, and I drop everything that was below 3 random features. And now we go to this guy. Okay, so in these cells, I reuse the splits I compute in the previous cell, and I take all the data, and I also discretize the actual features into 4 classes. So I have the population into 4 classes, and each feature into 4 classes. And compute confusion tables for every combination. And then I compute the mutual information for each of those, and I pick the maximum. So if I have this feature, it has 4 values, the target has 4 values, you have all these combinations of different tables, and I pick the maximum mutual information and say, well, this is how good this feature is. And thanks to the virtues of the IPython HTML display, then we get this nice table of good features, which I'll have a slide on it. And then this table of bad features. Yeah. So it's dropping things like Northern Cyprus, or population a certain year, or history of Hamburg. So these are features that are fairly rare. So because this is seeing how much information from one help you with the other, because these ones don't have much information to begin with, then mutual information don't like it. If you use other metrics like chi-square tends to love these type of small features, and that's what I didn't find it very useful for this data set. So these are features that are particularly good for this data set. The inverse of birthplace. So we can,
Yeah, so you use the neutral information. So like the intuition, like why not use like Gini or other stuff? What's the intuition behind it? And also, I think the radar class is actually has more information than the most popular classes. So like
well, I mean that depends on the data. In this case, the rare classes didn't help.
So like what's the intuition behind choosing those kind of metrics?
So the intuition for mutual information is this information theory about how much one feature helps you explain the other. Yeah.
So is it like a whole bunch of a subset of features you are checking how it is? You don't really ask why, is it?
I mean, what I'm doing is the contingency table. Yeah. So I'm seeing how one particular value correlates, it happens together with one particular value of the target. Yeah. The difference is that chi-square, for example, is pretty bad at predicting things when the total number of counts is, any of these numbers is less than 30. And here I have very rare features. Many of these features happen very little. So when I ran it, I was getting, my top features were really garbage. So
So you're comparing different, so you're grouping the values of that a certain feature can take, and grouping the values that your target can take, and then you calculate mutual information for each category combination, and then how do you aggregate this information
Max.
to find
Like I'm trying to see, I'm trying to give each feature the best chance.
Yeah.
Because seeing each feature independently is actually very poor. But one of the nice things about here is that you see the counts are all kind of at the top. So not dropping the counts when we saw in their analysis that were hurting was a good decision. They actually do help. But so overall it dropped 68 features, and the new feature vector ended up having 314 features. Another way of doing this sort of analysis of how well the features help is using Gini impurity, but just use it in a decision tree algorithm. So instead of using a decision tree for classification, you can use it, just plot the top level branches to understand which features the decision tree algorithm finds more useful. So here it starts from birthplace count, and then it goes to how many, if it's in a different country, number of offsets it has. These ones in gray are all related to cities, to countries. So you can see that countries is very important. Something that is also interesting is that then it's also looking to area total over there, area total over here, and over there is population density. So from here, from this decision tree, I have the idea that, okay, if you have the population density and you have the total area, that stuff is population total, right? So you can have a computable feature. And that goes into the last. Okay, and the last thing we are going to look is into try to make the categorical features more informative. So if you have a category like country USA, yeah, that's a very opaque category. It's a column that has zeros and ones. And from time to time it has a 1, and the rest of the time it has 0. And also for the overall feature that is country, it's not really telling you much. I mean, that information about what country is split into all these features. So this technique called target rate encoding tries to make the categories more informative. And the idea is to replace the category feature with the most common value of the target for that feature. So a good intuition for countries is that you are replacing that 1 for the average population of a city in that country. Yeah, so you are looking at all the rows that have a 1 there, so are all the cities in that country, and you take the average of the target value. This technique is quite popular, and it receives a lot of different names like categorical encoding, CFAR, correct firing rate, leave one out encoding. One of the main things is that you cannot use the target for computing it. So you have to use cross-validation to actually get it. Otherwise, you will be giving your target to the system. So here's a little example to try to ground things. So I have a feature with 3 categories, A, B, and C. In one hot encoding, this will be A, B, C with zeros and ones, and a target that is positive or negative. So if you get the counts, you see that A is with plus 100% of the time, B is with plus 40% of the time, and C is with plus 50% of the time. Instead of having this, you encode it as that. So now the system no longer knows whether it's A, B, or C, and if you were several that have the same number, end up being in the same. So it conflates categories to things that have the same number. So now this feature is a much more informed feature than the original one. It's putting the categories in light of the task. Of course, if the machine learning is good, it may do this type of modeling inside. And then all this is programmed in this cell, which is a little bit like the mother of all cells. So this is the compute feature of population density times area land. And so here is the part that it does the target rate encoding. And there are several things that are quite annoying about target rate encoding. One of them is that besides the defaults for changing the train data, you also need to have a whole one to change your test data. Yes, so you have to do it basically twice, one with false, another over the whole data set. And then in my data set, because I have it done in columns, then I have to kind of flatten all those columns into only one. And that is done over here, which is quite a bit of Python code. And at the end of that whole thing, you have the file. But because SVRs require scaling, you actually need to do this after you have scaled your targets. Otherwise, the scaling will kind of kill your whole thing.
So the balance between the test and the training set has to be pretty spot on. Otherwise, when you start modifying the test set, if there aren't the same numbers of features or the same number of values, say, then you're going to end up with 3 different categories in your test set and only 2 possibly in your 4 in your training set, because there isn't enough of a mix of data in both.
So the test set will be okay if it's small. but you do need quite a bit of a big train set. And more importantly, you need a lot of faults. So initially when I tried to run it first, I was using 2 faults. And 2 faults can produce a lot of, it can produce values for encoding that are very different, just by luck. And in one case, for example, it reversed the 1 and the 0, because the average were different in each side. And then that was destroying completely the signal.
How do you fix that?
You add more faults. So if you have 10 faults, then you have enough data on. You have 90% of the data, so that's much more stable on the averages.
Okay.
Still, on this data set, just using the TFE alone, the TRE alone, the target rate encoding, didn't help. It helped using it together with the original features. Like the SVR couldn't really use that number so well, but using it together with the 1s and 0s, then it did help quite a bit. So in the here in the notebook, you have these parameters here on top, and here you can change to keep the original columns or not, and use a single one or not, and the number of faults. We're going to play with this a little bit. The thing that didn't seem to help a lot was the computed feature, which was a little bit of a disappointment, but it's only defined for a quarter of the instances. I mean, you have to have the population density and the area total defined, and when it's not I added 2 computed features. One that says whether this one is defined, and the other one the actual value. My feeling is that because when it's not defined, the value is 0, that may not be that good for the SVR. It will be better to impute that 0 to the average population. That may be a little more helpful. So this is the last SVR. These curves all look very, very similar, and they don't look that much like it's really tracking the.
Plus the anomalies seem to be back near the.
I need to learn how to make all these graphs at the same diagrams, because this is going to 7, while the other one I think was going to 12 or something. It was really, really out of whack. Yeah, 12.
Right.
Yeah. So no, it's
right. Yeah.
But the implication is done from the figure, definitely. Okay, so to wrap up, so after all these cycles, so this to me is 2 cycles of feature engineering. Yeah, so I did 1 cycle where I did the error analysis and the counts and the dampening of the counts, and then the second cycle with the TRE, and I have at the end of the notebook a technique for trying to find which features will fail less under catastrophic failure on the feature set. So try to find a more conservative set of features. And that allowed me to find like a little more conservative set at the end. But just for the thing we saw today, if you want to do the final evaluation, if you have to build this featureizer end to end, you will need to do the typing of the columns, you need to filter. So if you want to have a program that starts from the raw data, from all the graph data, and give you back the features, then you have to do all these steps. You have to filter these features, you have to do the target rate encoding. And so one of the things when you do feature engineering is that it's quite cumbersome to keep track of all these things. I'm hoping that there will be more technology on this in terms of the process part. But well, that's the state right now. So there are several follow-ups on this. The main one is that the transformation of one hot encoding for relations was not that such a good decision. Yes, from the whole analysis, it's clear that it will be having much better to have a set feature rather than one hot encoding. So then you can have, for example, the C also will have multiple values for it. Right now, if you have something like C also Brazil for the first versus the second, those are separate features. And well, that's full modeling. The GPS coordinates were missing. Even though they are in the info boxes, DBpedia doesn't have it. And that came up while I was analyzing the data. They are in the cities 1000 TXT file. The other thing is that country seems to be one of the most informative features, and it's not present as a feature. Meaning, it is present as a feature, but there are plenty of countries that are not there. And then you can see that the system is picking them up from other sources of features that contain country information. Like see also list of cities of Argentina. Yeah. So to try to distill a high quality country feature from all these different sources can be very useful. And finally, there may be a way of doing the discretization together with the rate encoding directly. So when you have, we discussed that you have features that have maybe 2000 potential values, yeah? So you don't want to have 2000 columns. But if you do some sort of rate encoding of those 2000, then you can add them. So you basically can make the other category much more informative. Okay, so to conclude, next time you approach a machine learning problem, even though sometimes it's a little hard to convince management that you are sitting there looking at the data is doing work, but I once have a contract where I was saying, well, now I will spend a day doing error analysis. What are you going to do error analysis? Well, I need to improve the model. But you're not going to be programming. I know, but how do you want me to improve the model? I don't know, try different models as you guys do. I was like, try different models blindly? So, then I dropped that customer. Think about it as a matter of cycles, and also you need a lot of bookkeeping while you're doing these cycles. So you remember what process you did and what features you use. I mean, this type of things, what really work well, you're going to be doing a lot of backtracking. So it's better to spend a little more time note keeping and less time trying to reverse engineer what you did at 3 in the morning on a Saturday. And again, search for the best, prepare for the worst, try to also think of a more conservative feature set if you are really going all into feature engineering. And back to here. Questions, comments?
This is a lot of data, and it looks like you're trying to take the data, engineer it a bit, to come up with something that indicates size of population. Wouldn't it be easier to work from perceived features that create a population and then verify it with the data? Because once you have all this data, it becomes overwhelming. Like I've read it in the statistical analysis book once, you should always have an assumption first that you try to prove with the data, then look at the data and go, oh, I wonder what that means.
So at the beginning, in the exploratory analysis, I started with 10 cities. Yeah, so in line with what you are saying, I just look at 10 cities to try to come up with what things will help. There are a lot of relations on these 10 cities. The ones I chose to use, in a way, come from those type of intuitions.
And so I'm assuming these 10 cities were fairly diverse.
Yeah, they were a random sample.
Okay.
And then afterwards, I found that many of them didn't even have a population information. So the next stage was just to filter the ones that I couldn't predict or do anything with them. And then I did another sample of them, and they got actually much informative. Like the ones with high population had more relations and more things going on.
Right.
But yeah, in line with what you said, yes, to the exploratory analysis, I started with small sample and just have a feeling of what the data was about.
Right. Okay.
And And from the number of nodes you see, there are a few cities that have a little more nodes, but plenty that has like 4 nodes, so they're kind of empty. And that gives you a feeling for the data set.
There's kind of a thing in the field now, like automatic feature generation.
Mhm.
I'm sure you know about that. Like there's feature tools.
Mhm.
Some guys came out of MIT, and
Mhm.
it's, you know, they do exhaustive enumeration,
Mhm.
visually overt entity relations. There's another group in IBM in Europe. It's a bit more recent,
Mhm.
and using like recurrent neural networks to learn
Mhm.
functions. It's a complete mystery what it's doing. But then they run it on Kaggle contests, and it's like,
Mhm.
like they do very, very well.
Mhm.
Do you have any kind of like this is very, you know, traditional hand feature engineering?
But that's the book I'm writing is about helping people learn the traditional handwriting.
Okay.
I do have a chapter on no, I have a section on the advanced chapter on AFE on automatic feature engineering.
I was just wondering if you
I
had
cover.
anything to say about the automatic feature generation stuff.
I will doubt that we will work on this amount of features and data.
Yeah. I'm just throwing it out.
Oh,
It's
sure.
very
I mean,
interesting.
it's a
You're doing interesting work.
So this is a book for people learning machine learning. I will be surprised if the book will help researchers in the field. Yeah, I'm hoping they will help research in field to teach courses. But that work, the one I have seen. Okay, so now with my extremely biased opinion, and machine learning researchers are really good at picking the little thing where their algorithm works to publish papers. So yeah, so I take the results with a very so if that stuff was useful, I will
We're
use it.
using feature tools in practice, and it's
Uh-huh.
for our application.
How many features do you have?
100 or so to start
All
with,
right.
and then it goes up to about 1,000. And
I
then
mean-
we use XGBoost, and it just cuts them right back again.
Mhm.
I mean, it works. So.
I mean, if it works, we use it.
Yeah. I know it's not one or the other.
The this is more about how do you if you try to train people into doing the hand labor intensive stuff, how would you go about it? And half the book is case studies because to me the way to teach it is showing how it's done, and I mean you have some theory and some stuff and you can explain feature mutual information and stuff like that, but at the end seeing it all together is quite and the other things that I'm dividing, I have the notebook, but the notebook, I have no code on the book. So I refer to the cells and have the results so I can cover more stuff. And even that, 2 cycles of feature engineering take 20 pages. It's quite mind-blowing the amount of blah blah you need to add.
Just wanted to ask. Okay, so it sounds like error analysis is kind of a like flowchart, like you've used a lot. So when error happens, you blame. It's a blame game, right? Blame the model or blame the data features. Now you go down the path of blaming the features. So a lot of the technique they present is the feature kerning. So basically saying that we have got too many features, it's noisy, it's like causing issues. You mentioned about some technique for feature generation. So for example, understanding at first you're using hot encoding, and I think you were mentioned though you pick the top 80% that's representative. When do you know when you're not having, for example, you're missing features that you actually is not representative enough, it's missing. For example, there will be like cities in, let's say a specific example that you have cities in Wikipedia that actually, because you're doing hot encoding and truncating 80%, those 20% actually get cut off and those cities have no information whatsoever. So when do you know that you need to include back some of those information into those cities in order to, like, when do you know when to add features or when do you know when to cut features? I was wondering. Does that make sense?
Of course.
Yeah.
I don't know. But I think the most valuable part is people asking themselves that question. I feel these days, when I have seen people, they just try different algorithms. and tune the parameters of the algorithm. Don't even think about the fact that, well, maybe I am missing a feature. Maybe so to me that question is super valuable. Then how do you develop intuitions about in which moment this other, for example, if you do the feature selection and the other category comes to be dropped, that's a big red flag that other is grouping too much stuff and has junk inside. I mean, end up being a junk feature, but you know it's not junk feature because the other classes are valuable. So that should give you the idea that maybe you should expand it. But at the end of the day, these are intuitions that are built as a practitioner. But if you are not even asking the questions, then you will never get better at this game. A bigger question is whether do you need to study this at all, because deep learning doesn't need feature engineering, it needs architecture changes, and that's a completely different question, which I'm happy nobody asked, but I'm sure you were all thinking about it. So my take on the deep learning stuff is that by now we have some intuitions about feature engineering, and you can even actually train a person to become confident on feature engineering. Well, we have absolutely not much idea about deep learning architectures, which is what replaces the feature engineering in deep learning. So there was a time when we were doing machine learning that doing feature engineering was kind of shooting in the dark. Now we actually do have an idea about how the process works and which different heuristics work. Architecture or deep learning right now is quite like, oh, I put these 3 layers and it works, and then I put 5 and it doesn't. And the other part is, if you have a small data set and you want to use deep learning, I really want to see how that goes.
I'm able to hold these questions, like how do you changing the model, how does it affect the feature engineering? Because maybe some features work for some 3D model and not for based on how the algorithm works.
So if in some moment in your cycle you decide to drop the model, then you really go back to quite a stage 0. I mean, you have to rethink your features for the new model. But how to improve the model is covered in most machine learning books. I mean, that's really well understood, or at least there is plenty of material on that. That's why I'm not talking so much about drilling down on the model.
I'm wondering the target encoding, because you use the class and also the distribution of probability over the values. I'm wondering if by any chance we're overusing the data set itself.
Well, but you use out-of-fault encoding.
Yeah.
So you are doing across. So for example, for Chicago, you put the average size of U.S. cities without Chicago. Yeah. No. Okay. So imagine you have all the American cities, yeah, without Chicago. And then you take the average size of them. That will be the target rate encoding for Chicago. So that value, then it doesn't contain the actual population of Chicago.
That's a good question. That's actually
That's why you use this out-of-fault encoding. It makes the algorithm quite more complicated. You divide the training data into faults, like if you were doing cross-validation, but you only do that to compute the value of these features. It's a very common technique. It's OOF, and in the Kaggle message boards, everybody talks about it.
Can I ask a question about Watson, your time with Watson?
Sure. What do you want to know?
Well, it seems now, I mean, at the time when it first came out, it was so impressive, it's not even funny, but now it's being looked at, it was a little rigid, but the architecture that was used maybe was a little too restricted or too hand-encoded, if you will. Do you sort of concur with that, and do you see some of the newer techniques being a little bit more amenable to general knowledge?
Oh, I agree. I mean, I left the company due to that. It was like a one-trick pony for the show.
Right. Okay.
But so from there to do more interesting stuff, it was not. I didn't really see the path to that. But there was in '95. I read the communication of ACM had a special magazine on natural language processing, and it was saying that it wasn't unclear whether we needed better engineering or breakthroughs from linguistics or other topics to. And to me, the nice thing about the Watson project is that answer that question with better engineer was enough. Yes, we were just scattering. We have 2 days of error analysis, 20 people in a room projecting error by error, and just engineering the whole thing, and it worked. Even though when we started, I said it was never going to work. That was my claim to fame. And we throw 1 terabyte of RAM to the thing, and that make a difference. So there is some sort of scientific value on saying, well, engineering is all you need. So from that perspective, it was rigid and it was just good engineering, but that's not something to take for granted.
Very good.
Thank you.